to the session 2 of the unit 3 of our financial modeling course. In our session 2, we are going to consider the goodness of fit of our regression model or our model estimation. By the end of this session, you should be able to interpret the coefficient of determination from regression model, and you should also be able to explain the information criterion or as used in the diagnostic of the fitness of our model or the goodness of fit of our model. The coefficient of determination, or what we call the R square. In regression analysis, the first point of call for estimating or for diagnosing our model, that's the goodness of fit, is the R square. That is simply the coefficient of determination. The coefficient of determination, unlike the correlation, which is the R, measures the portion of the regression, which is the dependent variable or the variations in the dependent variable or the regression, which are being explained by the regressors or the predictor variables. The coefficient of determination is an overall measure of goodness of fit of the estimated regression line. So here, our coefficient of determination is simply trying to estimate or trying to explain how movement of the regression, that is the y variable or the predicting variable, is being explained by the independent variables or the predicting variables that we determine in our estimation. It should be noted that a high value of R square is not always desirable or does not determine a model fit. There are other goodness of fit determinations that we or diagnosis that we are going to use in our subsequent sessions. We should know that only R square is just among the most important model or goodness of fit models that we are going to use, but there are other ones, because just having a high R square is not in itself demonstrate that you have a fit model. There are other factors that we are going to consider in this session, because there is a chance that in the people mostly err, we make mistake in estimating our R square, because there is this analysis or there is this analogy that because the R square simply depends on the number of parameters that you are going to use in your estimation. The more you add or the more parameters you add in your estimation, the chance that you are going to get a higher R square is very high, which indicates that just as you add more parameters or more independent variables to this estimation or to the estimation of your model, there's a likelihood that your R square is going to increase, which could not be the case, always be the case that, or which does not necessarily mean that all the variables that you are adding to your estimation or your model add value, or they are statistically adding value or increasing the value of your model. So a high R square is not in itself an assurance or does not in itself demonstrate that you have a good model or you have a fit model. This is an indication that whatever variable we include, so it has already been established by a professor that we can even choose to add the sink in our kitchen to our regression model, and there is a chance that our R square is going to respond to this sink in our kitchen by increasing our R square or by increasing the R square of our model. Therefore, we have to find a way to, or we have to find a measure to limit the level at which we are going to add these parameters or these regressors in estimating our model. Because we earlier mentioned that in the ordinary least squares, the aim is to find a way to fit a model or to find an average value that can explain the behavior of the population or the behavior of the whole. So we find a sample that can represent the whole. So our aim is also to reduce the sum of squared errors. So the errors or the errors that we are going to achieve or we are going to acquire in our estimation, the hope is that we are going to reduce this error to the barest minimum. So to improve upon the model and correct this limitation, measures such as the adjusted R square are used in our estimation. The adjusted R square serves as a punitive measure. It serves as a punitive measure by reducing the value of the R square as more and more regressors are being added. So as it became real, or it was established that the more parameters that you add to your model, the higher your R square will become. Therefore, the adjusted R square was the adjusted R-square was introduced, which will serve as a punitive measure. So now our statistician or analyst will no longer add just measures, will no longer add just any variable to their estimation, but they will use or they will add variables that are quite important or relevant in the estimation, so in order not to find themselves into this punitive or in order not to be punished by the adjusted R-square, because the adjusted R-square is going to reduce as more and more values are being added to your model. Therefore, it is prudent to consider the adjusted R-square in analyzing our model. So here, as the adjusted R-square was introduced, there's now the need that you don't focus only on the R-square, which is the coefficient of observation, but you rather focus on the adjusted, because the adjusted rather reveal the most important, or it reveals the real coefficient of determination as to whether you are adding variables that are not important or that does not have any value or does not serve any purpose in the estimation, or the values that you are adding actually add value or are of relevance to your model or the estimation of your model. So here we have with us some equations that represent how some of the estimations in our models are being done, or the diagnostic estimations are being done. So here we have with the equation 3.2 up to equation 3.8, we are simply focusing on the estimation of the adjusted R-square. So you could see that this is the average regressant, which is mostly the sum of all the regression all over the number of observations, and where the y-hat, which we've already explained in our earlier session as the actual or the estimated, it represents the estimated regression, and the y bar is the average regression. So here in our equation we could see that this is representing the changes or the error term. This represents the error term or the error. So the estimate minus the average will give us the error. So this denotes the error or the error sum of squared. So this portion of the equation, which is equation 3.5, represents the error sum of squared, and the equation 3.6 represents the total sum of square, where we find the difference between the actual, which is the sum of the differences between the population, that is the population regression, and the average regression, that is the total sum of squared. And the adjusted R-square is being the R-square is being estimated as the error sum of squared over the total sum of squared, which is equal to 1 minus the total sum of squared minus the total sum of squared. So it is with this equation that we're going to estimate the R-square, but we have to understand that all these equations are just here to highlight as to how these equations are being, or how these values are being established. Just that in our estimation we are not going to estimate our models manually. We are going to do so with the help of analytical softwares or statistical software. Therefore we don't have to stress much on this portion of the equation, but we just have to have a fair knowledge about how the adjusted R-square is being estimated from the average regression to the differences between the estimate and the average regression, and the sum of squared errors, which is denoted by the equation 3.5, and the total sum of squared, among other equations. So other than the adjusted R-square, another primitive measure for the temptation of adding more parameters to increase the R-square is the information criteria. Information criteria are statistical tools that are used to evaluate and compare statistical models, including regression models, based on their ability to fit the data while avoiding overfitting. So the aim of the information criteria is to also punish the excessive addition of the parameters, that is the regressors. So here our aim is to have an information criteria that will help us to fit the data, or that will explain, or that will establish that the data set is quite fit, or it fits our model. So the information criteria will help us in evaluating and comparing statistical models, including the regression. So in our regression model we can also estimate our information criterion, which is we can use the Akai-Quay, the Hannan-Quinn, and the the Schwartz information criteria, among others. Information criteria contains two factors. So it contains two factors. That is a term that is a function of the sum of squared errors, so where we aim to reduce the errors in our estimation, and a penalty for the loss of the degree of freedom from adding extra parameters. So in our estimation of the information criteria, there's a chance that if you add more parameters, that is the more of the regressors in the estimation of the movement of the regression, there's a likelihood that you are going to find yourself among these errors or within this limitation, which will make sure that, or which will indicate that your model is not fit. So it will help us in achieving parsimony, or in having a simple model that can explain the movement of, or that can explain the movement of our regression without adding more of these parameters. So adding a new variable to a model will have two competing effects on the information criteria. That is, the sum of squared will fall, or the value of the penalty term will increase. So as you reduce your sum of squared by adding more of the parameters or more of the regressors, you don't have to forget that the punitive measure, which is the degree of freedom, will also increase. Therefore, the observation, the number of observations in your estimation will reduce. The objective is to choose the number of parameters that minimizes the value of the information criterion. So mostly in the information criterion, we always want to see a figure, or we want to see a negative figure. So in our selection, we have to make sure that we choose a model that has the information criterion with the least value in terms of negative values. So we have the Akaike information criterion, which adds a harsher penalty for adding more regressors to the model. So the Akaike information criterion, or the AIC, will adds a harsher penalty for adding more. So here our aim is to reduce the addition of regressors, because there are some values that do not explain the movement in the regression, but we are forced to add them because we want to have more, we want to achieve high R square, or the high coefficient of determination. So the Akaike or the Akaike information criterion will help us in reducing this number of regressors. The model with the lowest Akaike or Akaike information criterion is chosen. So we choose the model with the least AIC. So in our estimation of the AIC, we use this model. We use this equation, which is equation 3.8, is used in estimating the Akaike in our in-use application. We also have the Schwartz information criterion. On the other hand, it gives the harsher penalty for adding new regressors as compared to the Akaike. So like the Schwartz information criterion is an upgrade on the Akaike. So here the focus is to add even a harsher penalty on the use or the addition of new regressors without necessarily adding, which do not add value to our estimation or to our model. The Schwartz information criterion is defined by equation 3.9. So in comparing model for our goodness of fit, the one with the lowest information criterion is selected, as I established in the earlier or in the previous session. So we choose the one with the least or the lowest information criterion. So a model with the lowest information criterion will be considered as the best model. So table 3.3 and 3.4 are similar to 3.1, but the difference is that in table 3.1 we were having all the parameters, that is all the regressors that were estimating or that were explaining the movement in the regression. But in this table, that's table 3.3, here you clearly see we have eliminated the education and the other parameters that do not, or that were not significant in our estimation. So you could clearly say we don't have education anymore, because it was estimated that education do not play a role in estimating a customer's credit ratings or credit worthiness. Therefore, we have eliminated all these parameters, or we have eliminated that portion of the equation. So we have all other equations, or we have all other elements of the equation as or intact, or the other portion of the equation are intact, or they are still available. So these are similar to the other equation, with the exception that we don't have the education and the gender that were used in the earlier table 3.1. So in this table we no longer have education, because it was assumed that education do not play a role, given that it has a standard error that was greater than its coefficient, the coefficient, and also had a probability value which was above the our significance level of 0.01. Therefore, we now eliminate it in order to explain our model with that parameters that can clearly explain the movement in our models. So here our focus is to achieve parsimony. So here, by removing the education, we have now achieved a model that can best explain the movement in our regression. So this is similar to our previous slide, or our previous table, just as the so equation 3.4 also remove the other portion that was not segregated, that is the equation 3 point. So in the equation 3.3 we were having the gender, but in equation 3.4 we have upgraded this table by removing the gender, as the gender does not also play any role in estimating the model. Therefore, we only have the income portion, the student level or the student status, and the bank balance. So here we are assuming that it is only these three parameters, the income, the student status, and the bank balance, that can now explain the movement in the credit ratings, or that can explain the credit worthiness or the credit ratings of a customer, with the other elements of the equations also remaining intact as we saw in the equation 3.1. In summary, we've been able to interpret the coefficient determination from regression model, and we've been able to use the information criterion and the adjusted R-square to diagnose goodness or fit of our model. We have come to the end of today's discussion. Thank you for your attention.